discussing an essay we just published on Substack. The title is Energy is a Computer Science Problem. We argue that similar to Galileo, who used human observation to develop new theories in science, computer-generated simulation can be a new lens, a new tool to do science, in particular physics, and hence it can help us solve the energy problem. We argue that energy is in essence a material science problem. At least modern energy problems converge to material science problems. And material science is a discipline where iteration is key. In other words, you have to try to assemble elementary particles and elements and things along those lines in an optimal way to achieve certain design goals. And computers and computation in general can be very helpful in that process. So therefore, we suggest that the same way that Galileo and his contemporaries used human observation as a new tool for science and therefore freed themselves from scholastic doctrines, this new approach could help us accelerate material science and hence solve the energy problem. This is the Not Even Wrong podcast. It's April 30th, 2023. This is Krim Telko. For the day, the fund is up 2.5%. The market is up 80 basis points. For the year, we are up 32.7%. The market is up 8.8%. We're outperforming by 23.9%. So let's talk about the essay just published on Substack. The title is Energy is a Computer Science Problem. So what we do in this essay, we try to systematically explain what this title means. So we're really dissecting the title. We're starting with the energy problem. We're then defining the energy problem as a subset of the material science problem, and then we define that material science can really be solved most efficiently with new advances in computer architecture, software, and AI. And therefore, we conclude that the energy problem actually is a material science problem and hence a computer science problem. We then also, as another conclusion or insight, I think a really interesting insight is that the same way that the Renaissance, and we use Galileo as a symbol for the Renaissance, one of the big innovations of the Renaissance was to use observation, to use human observation as a tool for science. And what is human observation? Well, it's just a very dedicated computer, if you will. So it's a brain that is able to do analytics, and then we have senses, in particular eyes. And Galileo used telescopes, so we had enhanced eyes that helped us get to better science. And Galileo was the beginning, of the mathematical approach to its natural sciences and culminated in the Principia Mathematica by Newton. So we believe that today we are at a crossroads where something similar is happening. We have a new tool, a new telescope, and that is the computer. And we shouldn't just use the computer as a sort of adjacent tool to help us do whatever, data analysis and things along those lines, but actually have insights into nature by using computer-generated simulation. This is one approach. There's many more things that computer science can do, but we want to emphasize, and we're emphasizing in this essay, that it's certainly not a solved problem. So we need to do research in computer science. So this is the key. So if you're a computer science major, you're actually working on energy. I would say this is an insight. This is not something that most people on campus would agree with. So if you're looking at computer science today as a field which looks at the whole stack, and the way I define computer science, I follow Onur Mutlu from the Polytech in Zurich. He's sort of my go-to researcher when it comes to computer science. So I just look at his lectures, and what he does is he goes through the stack. He starts at the metal, at the actual physical substrate, for example, silicon or graphene or whatever that may be, and then he goes up the stack, the gates, the logic, the microarchitecture, the the interface between the hardware and the software, and then the higher layers of software all the way up to the application. So this is what computer science is. And you can do innovation across the stack. And I think this is key, that we can innovate across the stack, and we have to innovate across the stack. In particular, what Onur Mutlu is talking about a lot is the memory constraint. So if you tie this now together with our thesis that energy is a material science problem, the reason energy is a material science problem is that a lot of energy problems can be solved through iteration. In other words, you have, let's say you take a battery, you have elements like lithium, cobalt, and so on and so forth, and you try to combine these in the most optimal way to achieve certain design goals of the battery, right? So this iteration can be accelerated through computer-generated design, and the iteration itself requires new approaches to memory management, because iteration is very memory intensive. You have a certain computation, you then have to store the result, you have to then compute again, you have to compare the existing with the new one, and then store the better one, and so on and so forth. So there's a lot of memory back and forth, and this is what Onur Mutlu is working on in particular, where he's trying to find better ways to, let's say, do in-memory computation, or just move some of the logic into the memory, or not move as much memory back and forth from the processor to the memory and back, because again, this is power consuming, and this is also time consuming. I think research shows that up to 70–80% of time that certain workloads use is not being used for the processing, but for the moving of data, which is part of the problem that Onur Mutlu is trying to solve. And I think it's very much in line with our essay here, because if you want to iterate fast at low cost, and some of these design goals that I think are just common sense, then you have to find ways to do that. And that is a computer science problem. And once you solve those problems, you can then attach this to, let's say, material science, and do your work there, and then maybe find better ways to store, create batteries and things along those lines. So this is really the gist of our essay, and I think it's a very important approach, because it opens up new doors. For example, we suggest new research in academia. We suggest new ways to look at this problem on the business side, on the government side. If we start looking at energy from a material science perspective, things change quite a bit. For example, material science then becomes, I would say, a much more important discipline, and it should be. Also, energy is not just about building billion-dollar machines to iterate and do moonshot projects and things along those lines. It can be a lot more iterative, a lot more low cost, a lot more low intensity, and more iterative. And we've spoken about this many times in this podcast, that the key to disruption, the key to progress in general, is to find ways to iterate rapidly at low cost, and at low cost of error. This is also important. You don't want to have a situation like, for example, the nuclear fusion reactor, something we spoke about this. And by the way, this inspired this essay. This is just a tangent. We actually met Chris Young, a researcher at the Livermore Research Center, and he was presenting about the breakthroughs in the nuclear fusion that they're working on. And while we applaud a lot of their progress and all of that, we are still somewhat skeptical about these mega projects, because they don't allow for fast iteration. Their errors are because they don't have a lot of iteration, there's very few errors, there's very few opportunities to correct the errors, and so on and so forth. And the cost of error correction is very high. So my point here is, I'm closing the tangent now. You don't want to be in this position. You want to have a project where you can iterate fast. And computation is just another word for iteration. And math is helping you find shortcuts to this iteration. This is what computational science is. And we believe that there's a lot more upside if we start looking at the energy problem from a computer science perspective. We start finding this is not just some philosophical rethink of a problem or anything like that. Once you start looking at a problem from a different perspective, all kinds of new doors open. And this is exactly what happened in the Renaissance when the Galileo and his contemporaries started looking at the world through human observation. I mean, yes, it was a big philosophical leap forward in a sense that they were basically putting scholastic theories sort of on the back burner, and they were focusing on okay, this is what we see humans and so on and so forth. And this is now almost a step away from human observation. We say, look, there's only so much humans can build and see. How about we develop virtual realities, computer-generated simulation, and let things happen in that world. And the beauty is these things, these iterations can happen a lot faster. For example, just one example, imagine you're working on materials for a battery and you have this problem that you need to iterate. And this is something that Tesla, for example, or Cattle and all these companies are working on a daily basis, right? They're putting certain materials together, then they have to test them. They have to see how these materials will last over many, let's say, cycles, over many, in different types of temperatures and ambient environments and things like that. So there's a lot of design options. There's a lot of design. There's a lot of design vectors that can be changed. And if you have to do this in the physical world, it just takes a long time. And if you could do it in virtual world, you could potentially do it much, much faster at much lower cost. And then once you have something that looks decent on the virtual side, then you can implement it in physical world and then see how it works. So this is roughly the idea of the essay. Again, to summarize, just published on Substack, our new essay, Energy is a Computer Science Problem. Our main thesis is that similar to Galileo and his contemporaries in the Renaissance, who developed a new methodology for science, which was human observation, we suggest that computer-generated simulation can be a new lens, a new tool for science. And it can be, and it's a lot more than just a new lens. It also opens up new avenues, new doors of academic research. It changes the way people think about things, and I think that those are big shifts. Shifts like that can actually have very, very big impact. And we believe in this case, material science, it is, when you talk to practitioners, people at Tesla or people at the Lawrence Livermore Research Center, whoever works on big energy problems, it always ends up being a computer science issue because it's about materials, it's about the composition of materials. If you want to throw in superconducting, if you want to throw in electromagnetic propulsion, all kinds of either esoteric or whatever kinds of new energy solutions, new energy harvesting solutions are being proposed, it always ends up being some sort of material science problem in one way or the other. And this is why we believe that computer science can help, and that's hence the article, hence the title, Energy is a Computer Science Problem. Thank you.